Have you ever stared into a cup of coffee, watching milk swirl and dance in ghostly tendrils? That mesmerizing dance, that chaotic motion, is turbulence. And it's not just happening on your kitchen table. It's the same chaos that jostles airplanes, churns our oceans, and, as it turns out, sculpts the very galaxies above our heads. But now, for the first time, we're beginning to see this invisible cosmic turbulence in stunning detail, thanks to a groundbreaking new model created by astrophysicist James Beattie of the University of Toronto and Princeton University. His team's study, published May 13, 2025, in Nature Astronomy, offers a breathtaking look at the hidden storms that rage in the interstellar medium, the ghostly clouds of gas and plasma between the stars, and how they interact with magnetic fields to shape the cosmos. This isn't just another simulation. It's a scientific milestone, one that pulls back the curtain on the turbulent forces that build galaxies, trigger starbirth, and steer the evolution of matter across billions of light years. To understand the significance of this model, we need to understand the space between the stars, a vast, seemingly empty expanse called the interstellar medium, or ISM. It's not a true vacuum. Instead, it's filled with diffuse gas, plasma, and dust, forming the faint but vital scaffolding of the Milky Way and other galaxies. Imagine a fog so thin you couldn't see it, even if it surrounded you. Now imagine that fog stretching for trillions of miles, sometimes gathering into dense nebula, other times so faint it's practically indistinguishable from emptiness. That's the ISM. And while invisible, it's not inert. Every cubic centimeter of the ISM contains whispers of energy, ions and electrons dancing through electromagnetic fields, occasionally colliding, often diverging, always in motion. Over vast timescales, this movement isn't random. It becomes the underlying beat of cosmic evolution. It's in these interstellar stretches that stars are born, planetary systems are shaped, and supernova remnants expand like ink in water. Without the ISM, galaxies would be skeletal, stars hanging in space without connective tissue. Incredibly, this faint soup of particles carries magnetic fields. You wouldn't feel them. They're millions of times weaker than a fridge magnet. But in the vast vacuum of space, those magnetic fields are not just relevant, they're dominant. They act as invisible scaffolding, guiding charged particles and shaping matter. They can compress clouds of gas, spark the collapse of regions that give birth to stars, and help define the structure of galaxies. These magnetic fields also influence cosmic rays, the high-energy particles that traverse space and occasionally slam into Earth's atmosphere. Even our own planet is protected by a magnetic field, the magnetosphere, which shields us from solar wind and cosmic radiation. Without it, Earth's atmosphere could have been stripped away billions of years ago, just as it was on Mars. So when we talk about magnetism in the cosmos, we're talking about one of the universe's foundational forces, an invisible hand guiding the motion and birth of celestial bodies. That's where Beattie's breakthrough comes in. To make this model a reality, he and his colleagues turned to the Super-MUC-NG, one of the fastest supercomputers on Earth, located at Germany's Leibniz Supercomputing Center. This machine can crunch more than 26 quadrillion calculations per second, and Beattie used it to simulate something as ephemeral as turbulence and as complex as magnetohydrodynamics across multiple cosmic scales. Their model is revolutionary in both form and function. It's modular, made of interlocking virtual cubes, each representing a volume of space with turbulent plasma and magnetic activity. When stacked, these cubes form an enormous 10,000-unit simulation, capable of modeling the Milky Way's magnetic architecture. But the same system can be scaled down to focus on localized phenomena, like the solar wind or coronal mass ejections from the sun. This multiscale flexibility is critical. For the first time, scientists can simulate everything from small ripples in stellar wind to galaxy-wide flows of interstellar plasma, all within a single unified framework. And it's not just academic. Understanding these phenomena helps us decode the underlying physics of everything from black hole accretion disks to the early universe's inflationary period. The model even has applications beyond space, offering insight into turbulence in plasma confinement for nuclear fusion, or even the design of spacecraft shields against high-energy particle flows. Previous simulations have fallen short in one major area. They couldn't capture how magnetic fields evolve and interact with local density changes in plasma. Beatty's model changes that. By integrating the flow of charged particles with real-time magnetic field evolution, this simulation replicates how fields twist, shear, and stretch through the ISM. As denser regions emerge and expand, the model accounts for how magnetic lines of force respond, tightening here, loosening there, spiraling into filaments, or tangling into turbulent knots. These intricate structures are vital. They influence the direction and speed of cosmic rays, determine where stars can form, and shape the galactic ecology over billions of years. The simulations also show the ISM as alive, dynamic, and ever-shifting, an environment where even the faintest fluctuations can echo across light years and sculpt regions of future star formation. It also opens new avenues for investigating how supernova shockwaves interact with the ISM, how interstellar bubbles form around young stars, and even how entire arms of spiral galaxies bend and curl under magnetic stress. But the most jaw-dropping part of this study? The sheer aesthetic beauty. As Beatty himself puts it, "I love doing turbulence research. It looks the same whether you're looking at the plasma between galaxies, within the solar system, in a cup of coffee, or in Van Gogh's The Starry Night." This isn't just poetic musing. Turbulent flows in astrophysical plasmas do mimic the swirling brushstrokes of Van Gogh's iconic painting. Mathematically, they follow similar patterns. It's one of nature's most astounding quirks, that from subatomic scales to cosmic ones, the same swirling, chaotic elegance emerges. There's a universality to turbulence, a kind of cosmic signature that reminds us we're part of a much larger dance. In the chaos of fluid motion, we glimpse both randomness and structure, art and arithmetic. It's as if the universe expresses itself not only in stars and galaxies, but in the way milk stirs in coffee, in the crashing of waves, and in the spiraling arms of a hurricane seen from space. Of course, simulations are only part of the equation. To truly unlock the secrets of galactic turbulence, Beatty and his team need to compare their models with real observational data. Enter the Square Kilometre Array, the world's largest radio telescope, currently under construction in Australia and South Africa. Once operational, it will provide ultra-sensitive maps of magnetic fields across galaxies, detecting the faint signals emitted by spinning electrons caught in magnetic spirals. Pairing this data with Beatty's simulations will allow researchers to refine their model, verify their predictions, and maybe even discover new, unexpected behaviors in the interstellar medium. Other sources of data, including NASA's Parker Solar Probe and ESA's Solar Orbiter, will provide close-range observations of plasma behavior near the Sun, offering ground truth for small-scale simulations. And beyond Earth, future telescopes like the Vera C. Rubin Observatory and the next generation of space-based infrared arrays could bring a whole new level of clarity to our understanding of turbulence on galactic scales. It's not hard to imagine a future where simulations like Beatty's help us identify hidden patterns in cosmic data, guiding telescope time, space missions, and even the hunt for habitable exoplanets. This work is more than a technical feat, it's a philosophical one. We often imagine space as static and serene, but the reality is far more dynamic, a roiling, shifting ocean of invisible energy. And thanks to Beatty's model, We can finally map this ocean in motion, revealing the underlying mechanics of star formation, galactic evolution, and cosmic structure. It also has practical implications for life on Earth. Understanding how turbulence affects charged particles can help us better predict solar storms, protect satellites, and even improve nuclear fusion research, where plasma behavior is key to creating sustainable energy. Ultimately, this research deepens our appreciation of the universe's complexity and its unity. The same physics that drives swirling gas clouds billions of miles away also shapes the pattern in your morning latte. It's humbling, really. The more we look outward, the more we realize the fabric of reality is woven with recurring themes: motion, magnetism, chaos, and structure. From your coffee cup to the stars above, turbulence is everywhere. Chaotic, beautiful, and now, finally, understood in more detail than ever before. Thanks to James Beattie, the University of Toronto, Princeton University, and the mighty Super Mu-CNG supercomputer, we're now one step closer to decoding the cosmic storm that gave rise to everything we know. And if you think this was mind-blowing, just wait. There's so much more turbulence to explore. Subscribe now for more science stories that uncover the secrets of the universe, one beautiful mystery at a time.